Good morning. Let's continue our lesson. Chapter 33 Sound Waves. Today we want to talk about properties of sound waves. Sound gives interference and diffraction effects. Do you remember diffraction? Here is a case for diffraction. We talked about it before. Okay, so when a wave is moving and there's an obstacle or a small opening in front of the wave, what happens in this case? The wave will diffract. So if you are standing here and there's a radio here, so the sound can reach your ear. How? Because the sound wave, they can diffract. This is one of the properties of sound waves. Second one, interference. Interference, it means when two sound waves, they interfere with each other, two different sound waves. So also, sound waves can interfere. Sound waves obey the same laws of reflection as light waves. We talked a lot about the law of reflection of light. Here also, sound waves, they obey the law of reflection, so they reflect. So sound waves reflect from any surface. So also, sound waves, they reflect. Okay? They reflect and they obey the same law as law of reflection for light. A reflected sound wave is called an echo. So echo, it is the name for any reflected sound wave. But we have a case if the reflecting surface is nearer than 15 meters from the source of sound, the echo joins up with the original sound, which then seems to be prolonged. This is called reverberation. So we have echo, we have reverberation. Now they are the same. Both of them, we are talking about a reflected sound wave. But the difference that echo, we have it with large distances. But reverberation, when we are in a closed room, the distance between the source of sound and the reflecting surface is less than 15 meters. To understand more, let's watch this video together.
Does anyone know what reverb and echo are?
You know, who'll know?
Tell us, Mr. Audio.
When you stand on the rim of a canyon and yell, "Hello! Hello!" and you hear your word a second or so later, that's an example of echo. Essentially, it's the sound that's reflected back to the listener. There can be multiple reflections, as sound bounces off walls, floors, ceilings, and other hard objects. When these reflections arrive very close together, the listener no longer hears a distinct echo. This then is reverb, short for reverberation. It's what people hear when they sing in the shower.
So, too much reverberation causes what? Causes confusion. That's why modern concert halls are designed for the optimal amount of reverberation, so seats and some wall surfaces are covered with sound-absorbing material, okay, to reduce reverberation. Is this clear? Very important to know the difference between echo and reverberation. Let's continue. We want to talk now about speed of sound. When someone speaks, it seems to us that we hear the sound they make as soon as they make it. However, it takes a small amount of time to reach our ears. Why? Because the speed of sound in air is about 330 meters per second. Girls, do you remember the speed of light in air or vacuum? 3 times 10 to the power of 8 meters per second. It means 300 million meters per second. Look the difference between the speed of sound in air and the speed of light in air. Okay? Now, The speed of sound, 330 meters per second, it is the speed of sound in air when the temperature it is 0 Celsius. Okay? So it's not always 330 in air. No, it changes depending on what? On the temperature of air. It's 330 when the temperature of air is 0 Celsius. The speed of sound changes if the temperature of air changes, if it is more humid, and so on. So it depends on the temperature and also humidity. Let's see how. If temperature increases, speed of sound increases. Okay? This is the relation between temperature and speed of sound. When humidity increases, speed of sound increases. The last thing, when altitude increases, the height, what happens? Now we know that at high levels, always the temperature is less. So altitude increases, temperature decreases, so speed of sound decreases. Clear? So speed of sound in air again is 330 meters per second, but this speed only when temperature of air is at 0 Celsius. The speed of sound in air depends on so many factors like temperature or humidity. When temperature increases, speed of sound increases. So if they ask you, for example, in the exam, why these sounds seem clearer in summer more than in winter, what is the reason? The reason that when temperature increases, speed of sound increases. So in summer, the speed of sound moves faster. Okay? Let's continue. Also, speed of sound depends on the material through which it is passing. It's greater in solids than in liquids or gases because the molecules in a solid are closer together than in a liquid or a gas. Let's look here together at this figure. Now girls, at the beginning of this lesson, we said that sound waves, they need particles to be transmitted. Without particles, they can't move. So, if there are no particles, the sound waves cannot pass, cannot move through this medium, the same as, for example, vacuum. Okay? No particles, no sound. Now, when particles are closer to each other, the same as in solids, the sound will move faster. When particles are far away from each other, the same as gases, the sound moves slower. Why? Look, what's the difference? The particles here are close to each other. They are tightly packed. So, when the first particles here at the beginning, they start to vibrate direct, they will be in contact with the other particles or the next particles and they will cause them to vibrate. So the vibration or the energy will move very fast through them. But here in this case, look, the particles are far away from each other. So it will take more time until this one starts to vibrate and send the vibration or the energy to the other particles. Okay? Look here, examples. We said speed of sound in air 330 meters per second. In water, 1,400 meters per second. In solids, 5,000, 6,000. Look the difference between air and solids. Clear? Now, let's watch this video together to understand how, or to believe, not to understand, to believe that sound moves faster in solids. Sorry. Where is it?
Now sound is a disturbance. Now to prove this, what I've done is I've arranged these dominoes equidistant from each other, which I will call it as particles of the medium. And this here is a balloon which is going to act like the eardrum. Now I'm only going to disturb the first particle, and let us see if the disturbance reaches the eardrum. Now what you have seen is I disturb the particle, and each particle disturbed the next particle. Now the particles have not moved from their place. They are in the same place, but the energy has been transferred to the eardrum. So are you ready to sport? This is a race between solid, liquid and gaseous medium. Now see what I've done. This blue and purple dominoes, I place them close to each other, and this is going to be my solid medium, because in solid medium particles are closer to each other. Now coming to the red dominoes, this red dominoes, I place them at a slightly greater distance, and this is going to be the liquid medium. Now coming to the yellow dominoes, of course you have guessed by now, the yellow dominoes are going to be my gaseous medium, because here the particles are far away from each other. Now we are going to create a disturbance at the same time instant. Let us see who is the fastest. So let me begin the disturbance, and I'm going to start this particular disturbance at the same time instant. So now it is clear the disturbance travels fast.
Okay, is it clear now? I'm sure it is clear. The last thing for today is a simple experiment. You have to know it to know how to find the speed of sound in air. Focus, please. Let's watch together.
How do we measure the speed of sound using some wooden blocks and a wall? We take a measuring wheel to measure the distance between this man and the wall. Let's say that's 100 meters. We give this man 2 wooden blocks, or a wooden clapper if you got one. Then we stand right next to him and have our timer ready. When he claps the blocks together, the sound wave of the clap will travel towards the wall. It gets reflected at the wall and then travels back towards us so that we can hear its echo. So we're going to start the timer when he claps, stop the timer while we hear the echo. Ready? We have the equation speed is distance divided by time. The distance that the sound wave has traveled there and back is 100 times 2. The time we got is 0.58 seconds, so plugging everything in, that gives us 340 meters per second.
Okay girls, I want you to know why here she multiplied the 100 by 2, because speed equals distance over time. Okay, do you remember the meaning of distance? What is distance here? It's the path that the wave has taken here in this case. So what is the path? It's not only 100. Why? Because it's back and forth. It moves, then it reflects back. So 100 plus 100. So 100 times 2, it means 100 plus 100. Okay? But the time is one time, 0.58. It takes until it moves from here and it comes back to the same point.
The speed of sound. But the big problem is, human reaction time is 0.25 seconds on average. So how likely are we able to measure 0.58 seconds without any human error? To reduce human error, let's try this. Get this man to clap the blocks 10 times. After the first clap, the sound wave travels there and back. And when he hears the first echo, he claps a second time. After the second echo, he claps a third time, and so on. It'll probably take him a bit of time to get into the right rhythm for synchronization. Once he gets going, we will time 10 claps. Now back to the equation, speed is distance over time. Traveling there and back is a distance of 200 meters. And this time, we've timed a journey of 10 separate sound waves. So we have to multiply by 10. Dividing by 5.8 seconds, we get 340 meters per second for the speed of sound.
So it is better to find what the time for 10 claps. It's more accurate to get an accurate answer. We do this step. I hope the video was clear and everything was clear in this lesson. Thank you, girls, and good luck.